And it's a great pleasure to welcome Professor Vincent Lepetit, which will be the session chair of this session. Thanks a lot. I hope you enjoyed the session. Vincent, please.
Thank you, Francisco. Welcome everyone. So let's start this tracking and detection session. So we have 5 papers today. Let's call the first speaker, who is Richard. So he's going to present his work on optical gaze tracking with specially sparse single pixel detectors. So Richard, how to use the system now, so you can ask questions on the session Q&A, and then I will ask the questions directly to Richard myself. You can also use the chat in the application, but it's better if you can to use the question and answer on Wova. So if you can play the video from Richard.
Hello, I'm Richard Lee. I'm a PhD student at the University of Washington, and today I will be presenting our work on a new sensing technique for gaze tracking. This work was a collaboration between the University of Washington and Video Research and the University College London. In 2008, the United States National Academy of Engineering identified 14 grand challenges that will tremendously advance the quality of life of mankind. Among them is a challenge of taking virtual reality to the next level. As part of the challenge statement, a primary hurdle to solve is gaze tracking, which is required for many applications of VR. Indeed, many startups have since demonstrated their answers to this challenge. At the same time, large players such as Google and Oculus have also shown interest in this problem as well, developing their own solutions and acquiring relevant startups. Despite wide interest from so many players, gaze tracking still faces numerous issues before it can be widely deployed. As a result, we are motivated to develop the capabilities of gaze tracking in terms of accuracy, refresh rate, power consumption, signal processing, cost, and form factor. All of these factors are essential to move towards a practical and deployable gaze tracking system. Of course, we are not the first to be interested in this problem space. Previous solutions have largely used cameras for capturing images of the eye for gaze tracking. These systems, while generally effective, are often require not only the camera, but also a light source to maintain a robust signal in different lighting conditions. Processing entire images can also be very computationally expensive. We show one example of a wearable camera-based gaze tracking system commercially available from Pupil Labs. More closely related to our proposed work, single pixel detector systems use an array of single-point optical sensors such as photodiodes. By using only photodiode receivers and LED emitters as an alternative to a full camera and light source, Lee et al. Showed that it was possible to use small solar cells to harvest enough energy to power the entire gaze tracking system. In addition to developing sensing hardware and processing algorithms, also relevant to our work is the use of simulation as a way to better understand the physical response of light on an eyeball. We adopt a similar framework to Invisible Eye for informing the design of our own system. Finally, while more distant from our work, for completeness, we also describe two non-optical sensing approaches for gaze tracking. On the left, we have scleral search coils, which use a coil embedded into a contact lens as a means of magnetic field sensing. On the right, we have electrooculography, which leverages the fact that the eyeballs are actually charged spheres, such that eye movements generate a voltage across the nose bridge, allowing devices such as the JINS meme to measure the voltage difference for estimating eye movement. First, I will introduce the concept of single pixel detection of gaze. Normally, camera-based gaze tracking systems obtain an image such as this. Computer vision algorithms then extract relevant landmarks for estimating gaze orientation. However, we hypothesize that not every pixel in that camera image is required to make that estimation. In this image, the image of the eye is subsampled to 1% of the number of pixels, yet general features such as the pupil and eyelid are still visible. Even when the image is subsampled by another half, the pupil remains clear. The primary advantage of such a sensing technique is that since fewer pixels are sensed, then fewer pixels need to be processed, reducing computational requirements, then overall less power is consumed, addressing one of our main motivations for this work. In addition, by using only the amount of pixels needed for inferring gaze orientation, we could also potentially remove the sensing of any biometric information, helping to preserve the privacy at the hardware level. Towards this end, we developed an initial prototype in which we simply placed photodiodes and LEDs directly in front of the eye. While functional, this first test was unusable for any real application since it blocked the user's field of view. To mitigate the issue of visibility, we simply moved the electronics to the edge of the user's field of view in a ring form factor. However, the signals then became a lot less clear for inferring gaze orientation. A previous gaze tracking company suggested that placing the sensors underneath the eye would be sufficient. It is well known, after all, that human eyes have a tendency to be angled downward. However, we found that the signal was still not very clear, and we were inspired to do more foundational work instead. We took a detour from rapid physical prototyping and developed a simulation framework using a 3D model of an eyeball. We oriented the eye in every possible orientation, sampling light in the way a photodiode would, and discovered that human facial structures generally vary too much from person to person in real life for the simulations to be helpful for making concrete design decisions. However, we did develop 3 primary design recommendations to help guide future work. 1. Maximize the variety and sensing perspective. 2. Minimize emitters so detectors don't saturate. 3. Co-locate emitter and detector to maximize the signal. With these design recommendations in mind, we enhanced our system yet again, adding sensors to the left and right in addition to the bottom. We also included a camera and infrared hot mirror for debugging purposes. Finally, we arrived at the final design for NextGaze, featuring 8 photodiodes for receivers and 3 LEDs for emitters. To minimize saturation, only one LED is on at a time, while its neighboring photodiodes take the measurement. Here, you can see the NextGaze form factor and its operation in real time. The white dot is the target for the user to move their gaze to, and the green dot is the estimated gaze orientation. Using a multi-layer perceptron model, we were able to obtain an average error of 1.68 degrees and 400 Hz refresh rate while only consuming 16 milliwatts of power. Next, for reducing the number of components used, we leveraged a technique for duplexing LEDs such that they can be used for both emitting and receiving. In doing so, we developed the LED-to-gaze prototype, which round robins through the LED, with one acting as a receiver while the remaining LEDs are used to make light measurements. This approach also increases the flexibility of sensing perspective, since a single point can now act as both. At the same time, we also found that a simple Gaussian process regression model can be more effective than the previously used model, while also requiring less training data. This resulted in a slightly improved accuracy of 1.57 degrees. However, while both refresh rate and power consumption were compromised, we believe that improved engineering quality can improve both of these factors significantly. In conclusion, we have shown how the use of a simulation framework was used to inform the design of 2 functional prototypes, NextGaze and LED-to-gaze. The latter is also, to the best of our knowledge, the first system to leverage the sensing capabilities of LEDs for gaze tracking, reducing the requirement of an extra separate component for sensing as well. With respect to the initial motivating factors we presented at the beginning, we did not meet our expectation for accuracy. However, both systems did have sample rates of 250 Hz, and NextGaze consumed less power than 50 milliwatts. In using the Gaussian process regression model for LED-to-gaze, we have offered a computationally lighter weight alternative to neural networks as a modeling technique. In addition, by using less components, cost can be saved. And finally, the use of discrete components allows for more flexibility in placement and topology, enabling more acceptable form factors. Thanks for your interest and listening to this talk. You can find a copy of the paper and these slides at the link above. I also look forward to any follow-up questions and comments that you may send me to the email address above. Thanks again.
Thank you, Richard. So there are a few questions from the audience. So we'll ask the first one from Steve. So it sounds like you're losing the ability to acquire the size of the pupil and to track the face for expressions and calibrations. So is it correct? And so if it's correct, have you thought about how to add those back? So Can you estimate the size of the pupil or track the face, or is it something that you lose when you decrease the resolution?
Hi, can you hear me?
I can, yes.
Okay. Cool. Great. So, yes. So I think so. In our paper, we describe a lot of applications, and in particular, what levels of eye tracking features are required for those applications. And so, I think the most important thing is you should choose the tool on the device for your need, right? So, for example, if you're very interested in um, very biometric type information, trying to understand, get exact pupil size, then our system would not be appropriate for your application. In our case, we were specifically trying to find a solution for basic gaze tracking, where we just want the orientation of your gaze. So we basically are trying to optimize for this particular problem. It's definitely not a super general purpose technique for all applications. Yeah.
Okay, thank you. So there is another question. I'm not sure I understand the question, but how the pose of the camera and the LEDs influence the system? So is it important to place correctly the camera and the LEDs?
I'm sorry, I don't think I understand the question either.
So how is it important? So is the position of the LED important in your system?
Yes. So as we described in the iterative process, basically, both empirically and through simulation, we found that the placement of the LED is very important for essentially maximizing the signal, right? That's the most important thing. And so in our particular case, we faced a lot of issues with saturation and having the light source too close to the detector, or too close to the detector, or too many light sources on at the same time. So this is basically a big finding from the simulation part of our work.
Okay, thank you. So I have one question actually. So does it work also for, it looks like it works for an open headset. So not just a VR headset, which would be closed and where you will not have influence from the outside lights. So does it also work for augmented reality?
Yes. So we didn't report the results from basically some preliminary testing that where we went outside and so as you saw, we basically had two form factors, right? One was this mask that was the display agnostic, and then the second one was embedded into the VR headset. And with the first device, we did go outside and let sunshine try to interfere with that and everything. And basically, we selected components that specifically were in a different wavelength than basically infrared from sun. And so if you read the paper, you can see the components that we selected and how we mitigated those concerns.
Okay, so that's very good. So there is one more question. So how robust is your system to eye blinks and to different human anatomy?
So two questions there, right? One is the human anatomy. So that was the main thing that we found in the simulation. Basically, that human anatomy varies a lot from person to person, and if you only use one human model to try to determine the optimal position for everybody, that is very difficult. It will we cannot find a generalized based on one human model, we couldn't come up with it like specifically this is the answer kind of thing. So that's why we came up with like a list of design considerations instead. The other one is linking. And so our system is, so I'm not sure to reject linking. The tracking of the gaze itself is remains robust. So yeah, the tracking quality should be good, and we are able to reject blinks. Yeah.
Okay, thank you. So just one last question, because that's so from Mark on the eye tracking. So can you also estimate the depth of the gaze? So basically, the Z value on where the eyes are focusing.
Yeah, that's a really that's a really good and interesting question. So we did not try that specifically, but that is, you would imagine that it's theoretically possible because it's, similar to how camera-based systems do this. That said, that's definitely future work and worth looking into. Yeah, thanks for the question.
Okay, thanks a lot. So let's thank Richard for the presentation. And we can move to the second presentation. So from Etienne Dubo from University of Laval. So the title of the presentation is RGBDE Event Camera Calibration for Fast 6DOF Object Tracking.
Hi everyone. Today I will present the work RGBE Event Camera Calibration for Fast 6DOF Object Tracking, the first 6DOF object tracker using an event-based camera. This work was made in collaboration with Université Laval, INRIA, and Thales. Today, most 6DOF trackers are using frame-based sensors like an RGBD sensor. Those methods can have great performance for precise tracking with error in order of millimeters. Also, they have good robustness in occlusion scenario or with free interaction. However, those frame-based sensors impose a high data bandwidth and power usage. And because those trackers are limited by the frame information and don't have displacement information between frames, the performance of high-speed scenario is lacking. That is why, in our work, we combine our RGBD sensor with an event-based camera to improve the current 6DOF object-based tracking. Our contributions are the following. Provide a new RGBDE evaluation dataset with calibration between the RGB, the depth, and the event information. In second, we increase the object tracking performance on high-speed scenario by combining all modalities. An event-based camera is fundamentally different from a frame-based sensor. Instead of integrating light over a period of time and producing a frame at a certain frequency, as represented by the first row, an event camera works by sending an asynchronous stream of events in space and time. In an event camera, each pixel reacts individually to change in brightness when they occur. Each event contains a spatial coordinate, a specific time when it was triggered, and the polarity to indicate an increase or decrease in contrast. Because those are differential cameras, they do not produce events on a static scene, which avoid redundancy in the data. Also, event camera does not suffer from the motion blur effect event on a fast scene. In our work, we combine an event-based sensor, the Davis 346, with an RGBD sensor, the Microsoft Azure Kinect, which has a frequency up to 30 frames per second. An infrared filter is added in front of the event camera lens to avoid the unwanted events. This is mostly a problem because the time of flight depth sensor was triggering multiple events. Both sensors are calibrated spatially with common checkerboard method for the intrinsic and extrinsic parameters. Both cameras support hardware temporal synchronization, and therefore it is used to pair RGBD frames with events in time. Because we are the first to address this problem with RGBDE data, we capture our own test set. We captured 10 different sequences with more than 2,400 frames. We can see example of those sequences with a yellow overlay representing ground truth position. We annotate our ground truth with an ICP method using the render depth from a 3D model. For some frames, we refine manually when the 6DOF position was erroneous. For the training dataset, we choose to use synthetic event data because a large amount of data is required. The SEM simulator is used to generate simulate event on multiple displacements of a 3D model. Our experiments show that our network can be trained on simulate data only without being critically affected by the real statistic domain gap. Some data augmentation are applied to avoid the domain gap. First, we randomly sample the brightness contrast threshold used by the camera. By sampling multiple parameters, our method could work on multiple event camera without need to retrain the network. Also, we add random noise to the synthetic data to simulate the imperfection of the event camera sensor. Our method used two networks in cascade to compute the final prediction. First, our event network compute a coarse estimate of the pose given only event information. And second, we use a state-of-the-art RGBD tracker to refine the final pose. The tracker is executed every time a new RGBD frame is available, so the 6DOF position is updated at 30 Hz. For the event network, we start by accumulating all events since the last frame. Those events are then separated in multiple bins over the time. All events in the same bin are accumulated with respect to the polarity to produce multiple 2D images. Representation is called event spike tensors and has a dimension of x by y by the number of bins. The main advantage of this representation is to keep the temporal information while it can still be processed by standard CNN. Without the temporal information, it will be impossible to know the direction of the object without prior in the background. Our network architecture is based on DenseNet and is adapted from the frame network architecture. The main difference is that we learn a 1-bit convolution kernel that we apply on the temporal dimension. Only one kernel is learned and the weights are shared for each pixel. This allows temporal information to spread into adjacent bins. The output of our network is the 6DOF displacement of the object during the sequence of events. Then, this prediction is used to update the current position and render an RGBD frames of the object at this new position. The frame network predicts the 6DOF displacement between the render frame and the Kinect frame. Because the event network put the render position closer to the final pose, the second network focused on refining the final position on small displacement only. Also, this network is essential to avoid drift over time. In practice, we run this network 3 times to refine the final estimation. At each run, the render frame is updated with the last prediction. Note that the frame network approach is from a previous work of Garon and al. But our approach is not limited to the specific RGBD tracker and could be extended to any other RGB or IGBD tracker. Here is the quantitative result in translation and rotation on our test set. The x-axis corresponds to the displacement amplitude between 2 frames, and the y-axis the error between the predicted and the ground truth pose. We compare the RGBD-only approach in blue with our method in pink. You can see that the error is similar when the displacement is relatively small, but while the displacement increases on the x-axis, our error decreases compared to the RGBD-only method. Per frame error is great to quantify the precision error. However, it does not tell the whole story in a tracking scenario with continuous prediction. Therefore, we also compare the number of tracking failures on the same test set. Consider a tracking failure when the translation error is superior to 3 centimeters or the rotation error is superior to 20 degrees. When a failure occurs, we reset the current position to the ground truth and continue the tracking sequence. Here you can see the number of tracking failures between the 2 methods. We also simulate the impact of a lower frame rate camera while still relying on the events. We can see that the event information helped to reduce the number of failures, even with a reduced frame rate. In all those sequences, tracking failures are reduced by more than 60%. Here is some qualitative result on tracking sequences, comparing a method at the bottom versus the RGBD method at the top. As you can see, both methods can track the 6DF position in slow sequences. However, when the speed increases, the method has more difficulty and tracking failure occurs. Note that the sequences are shown at half speed. When the speed increases more, for RGBD e-tracker start having tracking failures. But as you can see, it still have good performance, even on challenging background as this checkerboard. Thank you for listening. You can visit our project page where you can find our evaluation code and our test set. For more information, refer to our paper or come visit us to the Q&A session.
Okay, thanks a lot for the presentation. So there is a first question from the audience, which is, does the proposed method need some assumptions on the shape or the texture of the tracked objects? So which kind of assumptions do you have on the objects?
Yes, can you hear me?
Yeah.
Okay, so yes, for this question, yes, maybe I was not clear on the presentation, but clearly this method need actually to have the 3D model of the object, which include the texture. So for the event network, we train specifically for one object. So if we want to change the object, we need to retrain the network. And it's almost the same thing for the frame network, but it could be used at some extent with other objects without retraining. But at inference time, you need a render of the object. So again, you can only track an object where you have a 3D model with the texture.
But I guess the question is also on, can you work with objects that are that have no texture, or objects that have a lot of texture, so with high frequencies?
We actually didn't test that, but our assumption is that it would work because maybe it will impact the precision, but for at least the translation, the event will still be generated when there's a difference in contrast in the background. So our assumption is it will work with the textureless object. Yes.
Okay, thanks. So there is another question, which is there any motion blur in your dataset? And if yes, how will it affect your method?
Yes, for the motion blur, we only use a Gaussian filter on the frame, RGBD frame, for create some kind of motion blur. So and for the event, we take the assumption as the event are generally fast enough just to avoid the motion blur. So we didn't generate at all any motion blur in the event.
And so I have one question actually. So the advantage of event-based cameras is that they are very fast. So can you still use CNN? So are the CNNs fast enough to deal with the events without slowing or decreasing the advantage of using an event-based camera?
Yeah, that's a really good question, and it's actually an open problem right now. because a lot of work use approach like we do, and we actually just summate to concatenate all events on the image, and we use a standard CNN. But some approach try to extend it to work with a spiking network, for example, and really gain the advantage of the event where you have almost no latency, and you could use directly the new event. But for sure, our approach is limited to the time interval where we produce our image.
I think for me it's fine. So I guess with maybe a fast implementation, so accumulating the events would work or would be faster with maybe some engineering, so optimizing the CNN, so that would work. So that is just that maybe you need some engineering. And maybe one last question. So in the interest of time, so what I know about event-based cameras is that they are pretty robust to poor lighting or saturated lighting. Is it really true, or what is your experience with that?
Yes, actually, event camera are a GR camera, and they're really robust to change of lighting. So in our small test set, we have one sequence where it's overexposed, and we almost see nothing on the frame sensor, but with the help of the event, we have better performance. But still, for our approach, it's still limited by the frame, at least for the precision of the final pose. So for our approach, the event only is not enough. So we are not really robust to overexposed scenes. But in general, events are really good for that.
Okay, thanks a lot. So in the interest of time, so we can move on to the next presentation, but that was very interesting. So the next paper is bundle adjustment algorithm from Lipozu. You can play the video.
Hello everyone, I'm Lipu Zhou from Magic Leap. Today I want to introduce our work on efficient planar bundle adjustment algorithm. The co-authors include Dan, Wei, Frank, and Michael Keith from Carnegie University. As we know, bundle adjustment is very important for SNAP systems. Nowadays, depth sensors are available for mobile phone and AR devices. Plans are widely used in some systems for various depth sensors. In the literature, plan-to-plan cost is generally used in some systems. The plan-to-plan cost is to calculate the difference between two plan parameters based on this equation. But there are two disadvantages for the plan-to-plan cost. The first is the plan-to-plan cost is not invariant to the rigid transformation. This can be seen from finger A. In finger A, pi G is represented in a global coordinate system, and pi S is represented in a local sensor system. When the global coordinate system moves from A to B, we find out the difference between pi S to pi G changes, but you can find out the point to plan distance does not change. So the other disadvantage for the plan-to-plan cost is that the plan-to-plan cost may introduce bias, and this can be seen from finger B. In finger B, pi G is represented in the global coordinate system, and the pi S1 and pi S2 are represented in local coordinate system S1 and S2 respectively. So here we will show these 2 point clouds are with the same noise. So pi S1 and pi S2 are parallel with respect to each other. So, but we found out the distance between pi s1 and pi g is actually smaller than the distance between pi s2 and and pi g. This is not because pi s1 is more accurate than the pi s2, and this is holding because the local coordinate system of s1 is closer to the global coordinate system G. This may cause the optimization algorithm push pi s2 toward pi s1. So this may result in suboptimal solutions. And so in this paper, we adopt a point to plan cost. So as we know, the bundle adjustment problem is to jointly optimize the 3D points and camera poses. So we divide a planar bundle adjustment problem is to jointly optimize the plans and poses. We in this paper we adopt the point to plan distance to construct the cost function. It has a board like this. So LM algorithm is generally used to solve the bundle adjustment problem. One important step of the LM algorithm is to construct this linear function. To construct this linear function, we need to compute the Jacobi matrix G and the residue vector delta. So when the number of observations is large, it will be time consuming to compute J and delta. So in this paper, we solve this problem. So here we show the structure of the Jacobi matrix for the observation of the J's plan at the highest pose. We can find out this is a very sparse matrix. So here we provide the partial derivative of the point to plan distance. So here CIGK is a constant vector during the optimization. We can stack all the CIKG24 matrix and CIG. Use this CIG, we can rewrite the Jacobi matrix here and as here as a matrix 4. So here we want to introduce the reduced Jacobi matrix. So we first introduce lemma 1. In lemma 1, we show that the CIG can be written as this, as QIG multiply MIG. So here MIG has a fixed form, and the QIG G multiply QIG is equal to I4, where I4 is the 4 by 4 identity matrix. Use the definition of MIG, we can divide the reduced Jacobi matrix like this 4. Here we just use the MIG to replace the CIG in the original Jacobi matrix. So use this definition, actually we can have this equation in lemma 2. Here we want to introduce another important concept, that is the reduced residue. Here we first provide the original residue vector. So for the reduced residue vector, we just use the MIG to replace the CIG. So for the reduced residue vector and the Jacobi function, Jacobi matrix, we have a lemma 3, which to say the multiplication between the Jacobi and the residue can be replaced by the reduced ones. Using the above 3 lemmas, we have theory 1. In theory 1, we found out for the planar bundle adjustment, we can use the reduced Jacobi matrix and the reduced residue vector to replace the original one. As the reduced ones are generally much smaller than the original one, the computational time can be significantly reduced. Specifically, the runtime for computing the reduced Jacobi and the residue vector and the multiplication is just 4 KIGs relative to computing the original one. Here, KIG is the number of points for the gaze plane and observed at the ice poses at the ice pose. So for the planar bound adjustment algorithm is pretty simple. We just use the reduced the Jacobi matrix and the reduced relative vector to replace the original one in the Elham algorithm. So we conduct a set of experiments to verify our algorithm. We compare our algorithm with reference 3, which uses the plan-to-plan cost. We collected 3 data sets by the library-based M6 device. This device also provides the trajectory. So table 1 lists the characteristics of these 3 datasets. We found out even the smallest one it has 7 million points. So we consider the accuracy and the robustness with respect to different levels of noise. So we also we use the absolute trajectory error to qualify the accuracy of the result. Here we list the results of our algorithm and the compared one. So we can find out our algorithm can generate more accurate results and can converge fast. Also here we provide the trajectory generated by our algorithm and the previous ones. Also we found that it's very clear our algorithm can get more accurate trajectory, and for some large noise, the previous algorithm cannot even converge. So in this paper, we present an efficient solution for the planar bound adjustment problem using the point-to-plan cost. We verified that the point-to-plan cost is more robust to initial errors compared to the widely used plan-to-plan cost. So thanks for listening my presentation. If you have a question, please feel free to contact us.
Thank you. Thanks a lot. So I have a few questions, and for the audience, don't hesitate to ask also questions on Rova or the chat. So it's interesting to see that there are still things to do in bundle adjustment. So I have 2 questions. I didn't understand what is Kij exactly in your equation. So basically the speed factor that you get. What is Kij in your formula?
Okay, can you hear me okay?
Yes, I can hear you.
Okay,
yes.
So Ki for the depth sensor at each pose for the plane can observe a lot of points. So Kij means the gaze plane observed at the ice pose. So there are Kij points on the ice pose observed at the there are Kij points on the gaze pose observed at the case pose. Yeah.
Okay, so the more planes you have, the faster or the larger the speed up is, if I understand correctly.
Yeah.
Okay, so that's a good thing. And I also didn't understand, or actually you didn't talk about it, how you get the 3D planes. How do you detect the 3D planes in practice?
For detect the 3D plane in our algorithm, we use the region growing method. We first estimate the normal of each point. Then we use the region growing to collect all the points with similar normal. Then we use Ransec to fit a plane from this casters.
Okay, so I see. And so you use LiDAR data, right? So you use 20 points or 20 or clouds of point clouds, basically, from a LiDAR. Is that right?
Yeah, yeah. So in our experiments, we use LiDAR, but we can also use RGBD sensor.
Did you try RGBD, you mean? Yeah, so that's, and do you think you could, or do you think about applying your method also to RGB data? What could you do with only color informations?
Our method did the depth the LiDAR or RGBD sensor.
No, that makes sense. Yeah. Oh, so yeah, I get it. Yeah. Thanks a lot. No more questions from the audience. I don't see any. So thank you, Lipu, and we can move to the next paper. So the title of the next paper is the next presentation. Yeah. Is learning bipartite graph matching for robust visual localization. And the presenter is Aileen Yu.
Hello everyone. Today the subject of my presentation is learning bipartite graph matching for robust visual localization. Visual localization aims to estimate 6-stop camera pose from a single image, which is a fundamental technique for many 3D vision tasks, such as SLAM, structural motion, and visual positioning systems. Feature-based visual localization firstly performs feature matching between 2D local features in a query image and 3D points in an offline reconstructed 3D model. Then estimates the 6-stop camera pose from the established 2D to 3D correspondences by solving PMP problem. The accuracy of estimated pose is closely related to the quantity of the correct matches. However, due to the limited invariance and the discriminative power of local features, large number of incorrect matches may exist under the challenge conditions such as seasonal variation, day-night change, and repeated patterns. Besides, a large number of true matches will be lost due to using local similarity to find the nearest neighbor. Learning-based localization methods proposed in recent years using deep neural networks to directly regress the 6-stop camera pose from a given query image. They do not suffer from the problem of local feature matching and are very robust in scenes with illumination change or textureness region. But its accuracy is unsatisfactory, especially for various AR applications. Another type of learning-based methods firstly regress the scene coordinates of query image and then compute the camera pose using PNP algorithm. These methods are more accurate than direct pose regression, but are hard to converge in large-scale scenes. Besides, the requirement of a large amount of training data limits their scalability and application. This is a traditional feature-based pipeline. To improve accuracy and robustness, many methods focus on using more discriminative local features, such as superpoint and detonate. However, there are many similar local patterns in real environments. Ambiguous matches are avoidable even using powerful learning-based features. This problem will be more serious when the matching is performed on a large-scale scene. In this work, we focus on feature matching and outlier filtering. We propose a neural network to deal with this problem. The network uses global information to eliminate the unreliability of local similarity. This greatly improves the recall of true matches compared to the heuristic ones. Given a set of initial 2D to 3D correspondences which are many-to-many, a bipartite graph can be constructed with the 2D points and the 3D points being the vertices, the correspondences being the edges. Taking the graph as input, f theta predicts the likelihood of being a linear for each edge,
and outputs an optimal one-to-one match. We call FCT as bipartite graph, neural network, or BigNet for short. The network can be divided into two steps. The first step is to predict the weighting vector W, which indicates the likelihood of being linear. The second step is to find out the maximum weight matching. Firstly, a bipartite graph G is constructed from initial candidate matches. The initial candidate matches are obtained by finding k-nearest neighbors. Then, the bipartite graph is fed into the network denoted as localization. As shown in the figure, the network contains three subnetworks represented by UNet, VNet, and ANet respectively. The input to UNet is the 2D point set U. UNet embeds the 2D point coordinate into D1-dimensional vectors. Similarly, the input to VNet is the 3D point set V. VNet embeds the 3D point coordinates into D2-dimensional vectors. For a specific edge EK, the feature vector input to ENet can be obtained by combining the feature vectors of the I's 2D point and J's 3D point out from UNet and VNet. The output of ENet is a t-dimensional vector, and a sigmoid layer on the right of ENet is used to ensure that each value of the output vector, lowercase w, is in the range of 0 to 1. Based on the weighting vector lowercase w predicted by the network G, a weight matrix denoted as capital W is filled according to the edge state E, and some field elements of the weight matrix are set to 0. Then the Hungarian algorithm is applied on this weight matrix to get the maximum weight matching denoted as capital M. The elements in vector S are set to 1 if they belong to the maximum weight matching, otherwise 0. We use sparse SF models to automatically generate the training data. For a specific image, we compute ground truth 2D to 3D matches from sparse SF models and randomly add a certain proportion of outliers. We use the most commonly used cross-entropy loss function for training. Tk, Sk, and Wk is tunable, predictable, and predict weight for case age respectively. We embed BitNet into a hierarchical visual localization pipeline. The whole localization process is divided into four modules, namely single retrieval, 2D to 3D local feature matching, finding maximum weight matching, and prior guided post-estimation. For query image, its global feature and local features are extracted. The global feature is used for image retrieval. Then we use co-visible information provided by the SLM model to expand the retrieval results. Both image retrieval and the expansion are called single retrievals. At the fine localization stage, the local features are used to establish 2D to 3D correspondences. Then BitNet is applied after the local feature matching to find the global optimal one-to-one matches and predicts the likelihood of being in linear for each match. Finally, camera pose is computed from these matches with predicted priors. We draw the inliers on the retrieval image and compare BitNet with the commonly used ratio test and cross-check. Our method can find more inliers, making the solved camera pose more accurate. This is the result on two benchmarks, Akindenite and Rosecar dataset. From this table, we can see that using single retrieval strategy can get a higher recall, and using BitNet can further improve the results under hard conditions, such as night and night rain. This is the result on Cambridge Landmarks dataset. BitNet used here is trained on the Akindenite dataset. While the evaluation is performed on the different datasets and a different type of feature, the improvement brought by using BGNet shows that the network not only has good generalization ability for different scenes, but also for different features. This is a simple AI application using the proposed methods. The left is the recovered camera trajectory, and the right is two frames of AI results. It can be seen that the recovered trajectory by our method is quite smooth, even the pose of each frame is estimated independently. This is a video demo in order to demonstrate the high success rate and precision of the proposed visual localization method. The pose of each frame is estimated independently without using temporal information and SNAM technique. The virtual objects in this video include tree, barrel, and box on the road, and the ISMA 2020 logo on the wall. It can be seen that almost all frames poses are accurately recovered. In summary, BridgeNet uses global geometric information to eliminate the unreliability of local similarity, which enables the localization to obtain more correct matches, and hence improves the robustness and accuracy of localization. In the future, other information such as appearance can be further used to improve the robustness. That's all. Thank you for listening.
Thank you. That was very interesting. So I think that's the first time I see an augmented reality movie with this kind of techniques. Actually, that looks very accurate. So there are some questions from the audience. The first one is why BGNet can improve the robustness under difficult conditions.
Hello, can you hear me?
Yes.
Okay. Yeah, it's a good question. We usually perform feature match by finding the nearest neighbor. This would make a large number of match lost. We record these true matches by finding k nearest neighbors. This would introduce a large number of outliers. So we use BGNet to predict the geometrically consistent one-to-one matches. At this stage, BGNet takes all matches into consideration, so it can effectively reject outliers and reserve inliers. Yeah.
That makes sense. Yeah, thanks. And the next question is, does your method run in real time?
No, the method cannot run in real time. It's run at about 4 to 5 frames per second. We think that in real AI applications, real relocalization does not need to be performed for each frame. It is usually combined with SLAM technique to track the camera pose in real time.
Yeah, no, I agree. Yeah, that makes sense. So there is one more question, which is how robust is the method to scene changes?
Yeah, it's very robust to scene changes because we only use geometric information. There's no appearance information to, for example, descriptors. So it is very robust in scene change.
But let's say that one building is or disappeared, is destroyed. How is it still robust to large transformation of the 3D scene, not just the appearance, but also the 3D geometry.
Sorry.
So if the 3D geometry change to some extent, so for example, if an object moves, is it still going to be robust?
Sorry, I cannot hear the question clearly. Maybe due to the network. Can you repeat the question slowly?
Yeah, I will try to repeat it slowly. What if the geometry of the scene change? So if, for example, if an object moves between your images, your reference images, and the query image.
You mean dynamic objects?
Not really. So if an object is in your reference image, but not in the query image.
Could you type the questions in whole?
Okay, I can try to type it in the chat. So so what if the 3D geometry change between your database of images and the query image?
If the geometry
Is it still robust in that case?
Oh, okay. It's okay. There's no problem. There's no problem because geometry is consistent. It's still it's learned from the pre-constructed dataset. If the dataset is too large, it can generate well to unseen things.
Okay, I see. Thanks. Maybe one more question. So you showed that your method generalized to new scenes. So do you train your method on only one scene, or do you use multiple scenes during training?
Yeah, in my paper, I have conducted experiments to show that the BaseNet is trained on AcademNet and can generate well to Cambridge landmarks dataset.
Okay, I see. Okay. Thanks. So thanks a lot for the presentation. So we can thank the speaker and move to the next presentation, to the last presentation actually for this session, which is object detection in the context of mobile augmented reality, and presented by Jiong Li. Jiong, so that's, yeah, if you can play the video, thanks.
Hi everyone, welcome to this presentation. My name is Jiang Li, a senior research engineer of augmented reality at Optical US Research Center located at Palo Alto, California. Today, I'm pleased to talk about our work, object detection in the context of mobile augmented reality. Object detection plays an important role in augmented reality, where virtual content can be associated with real-world objects to enable applications such as product recommendation for e-commerce and the textual and the graphical informational display for educational purpose. The motivation of our work is to boost the performance of object detection in mobile AR, as shown in this example of chair detection. Recently, tremendous progress has been made on object detection using neural networks. But there are still many challenges, like for the 6D pose estimation. Compared with 2D detection, it needs much more training data with 6D ground truth. And there are very limited recognizable object categories. For example, The new released Google's media pipe model relies on one known category to estimate its 6D pose. In terms of 2D detection in the context of mobile AR, the SLAM algorithm itself is computationally expensive, while object detection has a relative low accuracy. Consistency is also a challenge, which means a well-designed system needs consistent detection over a wide range of camera poses. Another challenging is arbitrary camera orientation, which we mean the camera pose may not align with the gravity. Therefore, objects are not always in their upright orientation in the picture, and that lead to less accurate detection too. This paper is about object detection in mobile AR. There are many existing work using semantic information for AR, like SLAM++ was published back to 2013 in 3PR, and some recent work were published in ISMAR and ICRA too. But how about the framework from AR to object detection? We observe that there is much less work talking about from AR to object detection. Our insight is that we leverage the information generated by an AR framework to solve the challenges shown in the previous slide and improve object detection with information provided by AR. We are interested in three kinds of AI information: 6DoF camera pose, 3DoF point cloud, and AR global coordinates, which represent pose, scale, and place. Now, please let me show you the overview of our framework here. While many research is focusing on deep learning models, we designed the framework based on our insights. To utilize such information, we designed those modules in green color. They can work with any 2D detection DNS and runs at less than 1 millisecond themselves. We tested the SSD model in our dataset, and it increased the MAP by 12.4%. First, I would like to briefly talk about image orientation correction. It's very natural to have it work in AR, since AR provides the direction and the magnitude of gravity. We use it as pre-processing the input images from AR cameras for the DNA models. Objects that are placed on horizontal surface will appear in their upright orientation after this correction. Next, I would like to talk about our per category scale database. Before going to the details, I would like to discuss why we need such database. It's because if we need to use 2D boundary box in AR world, we need to find out how to label the corresponding AR point clouds using such semantic information. The most accurate way could be use the 3D model of the object to estimate the 6D pose, and then find out all the point clouds within the shape at that pose. But such 3D model is not easy to get, and such algorithm is very computationally expensive. An approximation could be achieved by using the 3D dimension of the object to estimate the 3D center location of the object. However, it's still impossible to know all the object's 3D dimension data. Therefore, we define per category scale database that approximates object dimension. And we also fuse all the semantic information at this 3D center location into SuperPoint. Per category scale database does have some assumption that the object is in an upright orientation. Fortunately, that is true for many typical indoor items like furniture and appliance. And we don't need to assume the pose of the camera since we use a gravity sensor on the AR device to correct the camera orientation anyway. But we still don't know this object's complete orientation, like a thin slab can appear very wide or very thin in the image. Therefore, we only have 2D dimension as our database definition, the horizontal and the vertical ones. And the horizontal dimension combines the width and the depth of the object, which we mark it as W here. As you can see in this table, our database defines the maximum and the minimum scale for the horizontal and the vertical dimensions. The data mostly is from Wikipedia and the Common Sense. Next, I would like to talk about our scale-based filtering. While we use the point cloud to estimate the depth of the boundary box, we could calculate the physical horizontal and the vertical scales using the formula and compare them with the corresponding category scale range in the database to get the probability. Let's continue our previous example. And here, since the real airplane dimension does not match with the calculated one from the airplane labeled 2D boundary box, it has been removed. Now, unlike semantic map, our semantic mapping is based on superpoint. We use a per category scale database to estimate the 3D location of a 2D boundary box. The challenge is to fill the semantic information in the AR environment, where the user may randomly view the scenes. That means it may not be a good idea to learn the semantic map directly from the input images, because the viewpoints of those images may not have a uniform distribution. Instead, our superpoints will integrate the historical camera view information, where the objects has been observed and what their scales on the image. Basically, if the similar view has been detected and share the same results, such extra detection will affect the score less than the first detected result does. Our scores will record such few different camera view angles for all the detected object categories into the list of scores. Here, we continue the example from previous pre-processed image. The first positive laptop happened only around this camera view. Therefore, it has a low laptop score as a superpoint, and then it is removed by a predefined threshold value. Combine all those three models, we compute our final output. And we show this example again to display the function of each modules. Now let's talk about the evaluation. Our approach does not need extra data for retraining the DNA. Unfortunately, none of the popular image datasets for object detection provides a 3D sparse point cloud and the camera pose information acquired by an AR framework. For this paper, we collect a new indoor dataset for evaluation. Here are some statistic information of our dataset and some examples where you could see some rotation where the user holds AR-enabled phones to scan real rooms. Here are the tables of the test results, where you could see the dramatic increase, about 12% precision rate, although the recall rate decreased 4%. In addition, we also tested the new release Google Media Pipe 6D model on our dataset and get 14.4 average precision rate, which shows a challenging of our dataset. Last, we list some limitation and the future work here. For example, truncated objects and the dynamic environment are still challenging. AR point cloud from commercial AR framework lacks temporal correspondence. And we also have some future work listed here. You can find more details in our paper. Thank you very much.
Thanks a lot. So if you have questions in the audience, don't hesitate to ask them on WOVA. Maybe one first question. So is your dataset publicly available?
Hi, yeah, can you hear me?
Yes.
Thank you. No, not yet. Right now, our data set is not public.
And do you plan to release it or is it private?
Yeah, I think we are going to publish data because actually we scan some private real rooms, so we need to sign some forms. It's
No,
not
you have to
outside.
yeah. You have to be careful, yeah. Also, you can, you should also release, I guess, the orientation of the image, and so that's what you capture and what you use in your method, because that would be an interesting data set. if I understand correctly, so you average the dimensions that you predict for the objects. So how do you do the average exactly? Or is it correct? And how do you do the averaging?
Um, sorry, I don't understand your question.
So you have multiple detections of the same object. Do you merge these detections to get a better estimate of the size of the object?
Yes. So actually from the typical deep learning models, they are like, for example, top 10 guess of the image. So we'll have multiple boundary boxes. And our pipeline will take all those top 10 or any predefined top n number of the boundary boxes with the AR station information, like the point cloud or pose, to use our pipeline. Our pipeline has three components. They work actually independently. So each component in our pipeline can improve the accuracy. So we show all the separate results in the paper as well. And we also show the overall um, algorithm, the frameworks can
Say a few words on detections together.
how I utilize the detection results from the models.
But when you have multiple detections, how do you merge them into to have a better estimate of the size of the object? So let's say that you have 3D bounding boxes, if I understand correctly.
Yes.
How do you average the bounding boxes?
Oh, the size that's the second component we discussed in this video. That's object category scale database. So basically, we have a kind of pre-knowledge. We know how this object category size should be. For example, if we have a chair there, the height of the chair should not be like, for example, larger than 2 meters. So when you have a bounding box coming with a 3D data we estimate, actually it's from the AR session. So we will, based on the depth of this 2D boundary box, we can compute the height of the 3D boundary box. So actually here we are not trying to estimate the actual size of the 3D boundary box. We just compute it from the kind of roughly estimate the height of the boundary box. And we compare this roughly estimation with our data set. Like I said, for example, a chair could not be larger than 2 meters. So if your boundary box told me that your chair somehow is larger than 2, like for example, 3 meters, so we will lower your probability based on that component. But we actually does not provide a more accurate estimation of your object size. We just roughly compute the size because the AR session right now can have only the sparse point cloud, so we cannot estimate the size in a very accurate way.
No, that makes sense. Yeah, thanks. So, and maybe one more or one open question. So you use one angle from the mobile camera to rotate the image. So you have this angle, so the in-plane rotation that you can get, so to rectify the images. Actually, there is one more angle that you can get, which is, I don't remember what it's called, so maybe the tilt, but there is one more rotation that you get from the mobile camera. Do you think you could also exploit this information?
I would say yeah, that's possible. Right now, we are actually expecting there are more and more information from the public AR SDK, and there are like from the LiDAR. We are expecting next year there will be more LiDAR sensors in the market, and we will have more dense point clouds too, which could further improve our approach.
Okay, thanks a lot. So that was my last question. So that was also the last paper of the session. So we can thanks all the speakers again. So that's there is a clap option in. And I think we can also thank the organizers for ISMAR, because that was my first experience with this system, and that was actually very interesting. So I tried, I had the opportunity to try many online conferences this year, and this one was actually the most interesting one. So that's so thanks also to the organizers. So that was the last session for today. So that's I can wish you a good night if you are in Europe, good evening if you are in the Americas, and maybe a good day in Asia. I hope I don't forget anybody. So thanks a lot.
Thanks, Vincent. Indeed, it was a great day. Thanks a lot, everyone, for being here. This concludes our second day of ISMAR. We wish you a great day, as Vincent mentioned, or a great evening. See you all tomorrow. Thanks a lot.